going to talk about how to work with radicals. And if you are not entirely familiar with this, please watch this video several times because we're going to use these techniques for the rest of geometry. And you'll use them again in Algebra 2. If you also need a review on exponents, one of the full videos of this can be viewed on my YouTube page. Just look up exponent and radical review, and you should be able to find it. Ask me if you have problems with that. So let's talk about it. What's up with these roots? So sometimes people will refer to radicals as roots because we'll have square roots and cube roots and fourth and fifth roots and all that kind of stuff. So let's start with the simple ones. We're just going to talk about square roots in this. And I'll use the term roots and radicals interchangeably depending on what mood I'm in. So, okay, the first question to ask is what times what equals 25? Well, we know that 5 times 5 equals 25. So 25 is what's known as a perfect square. And a perfect square is a number that results when we take two integers and we multiply them together. So some other perfect squares might be 1, which is 1 times 1, 4, which is 2 times 2, 9, which is 3 times 3, 16, which is 4 times 4, 36, all those types of things. Basically, if you looked at a multiplication chart where you have numbers on top and the side, and you multiply the side number times the top number and you get a number in the middle of the chart, that diagonal line with 1, 4, 9, 16, 25, 36, all the way up to 144, that is your list of perfect squares through 12. So, when we say, can you find the value of the square root of a perfect square, we know the value of the square root of 25 is 5. We know the value of the square root of 36 is 6. So the square root of 6 times 6 is 36. Now what that means, it's not 36, what am I thinking? It's just 6. So the square root of a number squared is whatever that number is. So how can you find the value of a square root that's not a perfect square? Say the square root of 12. Okay? Well, you might say, well, I could just put that in my calculator. And you could. And you would get an approximation of that number. And if you put the square root of 12 into your calculator, let's see what you would get. Bringing up my calculator here. You would get about 3.464, and that keeps going on and on, right? So if we take and say, wow, that's about 3.5, right? Then all the other values of the numbers beyond that get taken away and just approximate it out to that 0.5. Okay, so it's an approximate value of that square root, but it doesn't encompass the whole number. So what we want to teach you to do today is to deal with square roots without finding approximations with your calculator. So we've talked about the approximate value of square roots, right? Well, it's close to the real value, but like we showed with our 3.4641101, and it just kept going on and on, if we approximate that to about 3.5, then all this value of the number is taken away. And you say, well, that's just decimals, it's small numbers. But when you talk about that, it still has value, okay? So we're going to talk more about actual square roots. So we want to keep the whole real value in a reduced form that's as compact and as much outside the radical as we can. Okay, so we have approximate and actual numbers for pi, right? Well, roots and radicals are going to work the same way. And we're going to show you how to do that today. So when dealing with square roots, we want our final answer to be in simplest form. And what simplest form means is we want as much of the number that actually has real value outside the square root, to the left of the square root. Okay? The number under the sign, under the square root, must be a prime number or the product of two or more prime numbers, okay? So, like square root of 3 and square root of 6, those are in simplest form, because square root of 3 is prime, and square root of 6 is just square root of 2 times 3, right? Because 2 times 3 is 6. Now, square root of 12 is not in simplest form, and let's look at why. So square root of 12, if I break 12 down into a number tree, I get 4 times 3. 4 is 2 times 2. So square root of 12 is actually square root of 2 times 2 times 3, right? Well, what's the square root of 2 times 2? Well, it's just going to be 2. Now, we can't really talk about how to do these properties of square roots without talking about the fact that I can have numbers under the square root, right? And this square root of 12, let's make some more room here. I can break that apart into the product of the numbers that make up 12, okay? And that's nice because once I do that, I can also break it apart even further. I can say the square root of 2 times 2 times the square root of 3. Well, the square root of 2 times 2 is just going to be 2. And we're left with the square root of 3. So now that is 2 square root of 3. Notice the only thing left under that square root is a prime number. And the number outside it is a real number. Okay? Or a rational number, I should say. They're both real numbers. Okay? The number under the square root is an irrational number. So let's learn how to do this. We want to find the square root of 72. So I'm going to break 72 up. 72 is 8 times 9, right? 8 is 2 times 4. 9 is 3 times 3. And 4 is 2 times 2, right? So that means that my 72, square root of 72, is equal to the square root of 2 times 2 times 2 times 3 times 3. Take a moment with your calculator. Multiply 3 2's together and 2 3's together. Make sure you get 72. You should. No problem. So we know that if we find number pairs under here, those form perfect squares. And the square root of a perfect square is a rational number. So the square root of 2 times 2 is like square root of 2 times 2. We have another square root of 2 and a square root of 3 times 3. Square root of 2 times 2 is just 2. Square root of 3 times 3 is 3. And we're left with just a prime number under that square root. So the square root of 72 is really 6 times the square root of 2. Now, this is really easy to check on your calculator. If you look at the square root of 72's approximation on your calculator, and you take the square root of 72, you should get about 8.485. Now if you look at the square root of 2 and multiply it by 6, you get the same thing. And you know that you've simplified that radical properly. Okay? Some calculators have the ability to simplify radicals without losing the radical form. But this is only a check. This is just an approximate value. I want to see the real value for your answer. So I want you to know that the square root of 72 equals 6 times the square root of 2. Those are equivalent forms. So let's do some example problems. We already did the square root of 12. My font does not like to put that top bar on my square root, so I'll add those in. So remember that broke down into 4 times 3, and 4 breaks down into 2 times 2. Here we have a pair that we can pull out from underneath that radical because the square root of 4 is just 2. So that leaves us with 2 square root of 3. Now let's look at this. Negative square root of 24 is really like saying negative 1 times the square root of 24. Okay? So let's break 24 down. 24 breaks down into 4 times 6, right? And 4 breaks down into 2 times 2. 6 breaks down into 2 times 3. So what I really have is negative 1 times the square root of 2 times 2 times 2 times 3. I'm looking for perfect square pairs, right? Square root of 4 is going to be just 2. I have no more pairs left, so now I have just negative 1 times 2 times the square root of 2 times 3, which is 6. So this ends up being negative 2 square root of 6. Let's do the same thing for negative 3 square root of 80. 80 breaks down into 8 times 10. 8 is 4 times 2. 10 is 2 times 5. And 4 is 2 times 2. So I'm going to create some more room for myself here. So negative 3 square root of 80 becomes negative 3 times 2 times 2 times 2 times 2 times 5. And if we look here, we've got 2 pairs of 2, right? So that's 2 4s, right? What's 4 times 4? Well, that's 16. What's the square root of 16? That's 4. So we end up with negative 3 times our 4 times the square root of 5. 5 is still stuck under that square root. So we end up with negative 12 square root of 5, being the equivalent form of negative 3 square root of 80. See how what's left under the square root is a prime number or the product of 2 prime numbers, 2 or more prime numbers. We can have as many prime numbers as we want under there as long as they're different from prime numbers all multiplied together. So let's look at the next one, and I know I keep giving you big numbers, but I want you to see several examples of this. So square root of 196. And let's see, I'm trying to find different numbers that it divides into. And, oops, that's going to equal 4. So 96 divides by 2 into 98, which divides by 2 again into 49, which is 7 times 7. So this is nice. We end up with 4 times the square root of 2 times 2 times 7 times 7. Square root of 2 times 2 and the square root of 7 times 7. That leaves me with 4 times 2 times 7. And there's nothing left under the square root, so we no longer have a square root. So 4 times 2 times 7 is going to be 56. So 4 times the square root of 196 is 56. And if you'd put that in your calculator right away, you'd have seen that anyways. Now, let's talk about adding radicals, because sometimes we need to add terms that have radicals in it. And it's just like adding variables. Remember how we have x plus 2x, and that would be 3x's. Well, as long as the number under the radical is the same, we can add them together. Let's see here. I'm seeing something that is oh, here. This is going to get confusing. I just noticed this. These are tick marks here. They are not minus signs, and I was confusing myself. Okay, so x plus 2x is 3x. Likewise, if we have 1 square root of 5 plus 2 square roots of 5, that would be 3 square roots of 5, right? So radicals should be treated exactly like variables. They must be in like terms, meaning the same number under the radical in order to add and subtract them. Now always simplify or reduce your radicals before trying to add or subtract them, and we showed you how to do that on the previous slides. So here's some example problems. Here we have the square root of 20 minus the square root of 45. The square root of 20, that's going to be 4 times 5, right? 2 times 2. So this is going to equal the square root of 2 times 2 times 5 minus, this is 9 times 5 is 45, and 3 times 3. The square root of 3 times 3 times 5. Here we have a pair we can pull out, so that's 2 square root of 5. Here we have a pair we can pull out, so that's 3 square root of 5. 2 square roots of 5 minus 3 square roots of 5 leaves me with a negative 1 square root of 5. Okay. 54, square root of 54 times, or minus the square root of 96. Now, if we recall, 9 times 6 is 54, and 3 times 3, 3 times 2. Notice I have a pair of 3's I can pull out. So this becomes 3 square root of 6. And this is 12 times 8 is 96. 4 times 3, 4 times 2. Oh, now here I see I don't always need to break it down into the perfect squares. I have a pair of 4's that I can pull out. And I'm left with 2 times 3 under the radical, which again is 6. So this is going to leave me with negative 1 square root of 6, or you can just leave it as negative square root of 6. Same with this one up here. It could be negative square root of 5. Now let's add. 27 is 9 times 3, right? So what's the square root of 9? Well, that's 3. So 9 breaks down into 3 and 3, and we have a pair of 3's we can pull out. That becomes 5 times 3 square root of 3. 75 is 25 times 3. 25 is 5 times 5. So here we have a pair of 5's that we can multiply by our 2. And we have a square root of 3 left over there too. So that becomes 15 square root of 3 plus 10 square root of 3, which is just 25 square root of 3. Let's talk about how to multiply radicals. Now we have done a little bit of this, but when we're multiplying radicals, we want to group the numbers on the inside of the radicals together and then multiply. And if there are numbers on the outside, we're going to multiply those together. And if any of the numbers underneath or inside the radical can be reduced, we want to do that as well. So let's look at this first example. There we go. So this first example says 2 square root of 3 times 4 square root of 5. Numbers outside the radical get multiplied outside the radical. The numbers inside the radical get multiplied inside the radical. So 2 times 4 becomes 8. 3 times 5 becomes 15. 3 and 5 are both primes, so we don't need to reduce anymore. Now, sometimes we will need to reduce. Here we have 2 square root of 2 times 4 square root of 10. The 2's and the 4's, again, go outside. But underneath the radical, if we break 10 down, that becomes 2 times 5. And that 2 from the 10 multiplied by the 2 over here creates a perfect square of 4, right? So when we bring that 4 out from underneath the radical, it comes out as a 2, because our 2's get multiplied. Square root of 4 is 2, and 2 times 8 becomes 16, and then what's left under that radical is now in simplest form. So let's do some more example problems. So 6, we recognize, is 2 times 3. So when we multiply this all together, we'll have 2 times 3 times 3. That 3 can come out, and we're just left with 3 square root of 2. Here we're multiplying square root of 15 times the square root of 3. We recognize that 15 is really 3 times 5. So when we multiply these together, we'll have 3 times 5 times another 3, which gives us a pair of 3's we can pull out. So 3 square root of 5. When we break down square root of 8, we see a 4 and a 2. Break down 6 and we see 2 and a 3. So we'll have 3 times 5 on the outside. And on the inside of the square root, we'll have 4 times 2 times 2 times 3. Well, this 2 times 2 is a 4 times 4. So what's the square root of 16? That's going to be a 4 that we bring out. So this is like having a pair of 4s. Okay? So we end up with 3 times 5 times that 4 we brought out. It's just a square root of 3. And this is 20 times 3, which is 60. Square root of 3. So some of these problems can get kind of weird. Again, if you have questions on which calculators might be able to help you with this, or you want to check the decimal form of all of these, I would highly recommend that. Dividing radicals is the most complex thing that we'll do with this. When dividing radicals, you must move the radical from the denominator. This process is called rationalizing the denominator. Okay? So we multiply the radical. We multiply by the radical on the top and the bottom of the fraction. So this creates a different form of the number 1. Okay? So we want to make sure that our radicals always have a rational denominator. Okay? No radicals should be in the denominator. No square roots in the denominator. Here's what this looks like. And this is the first problem for this. We're going to do this one actually down here. So 5 divided by the square root of 2. We're going to multiply by the square root of 2 over the square root of 2, which is just 1. And we can multiply a fraction by 1 and not change its value. But if we notice on the top, this becomes 5 square root of 2. And the square root of 2 times the square root of 2 is just 2. So 5 square root of 2 has an equivalent value of 5 square root of 2 over 2. Now let's do this next one. Here we multiply by the square root of 2 over itself again. And this leaves us with 4 square root of 6 over 2 again. Now notice we need to reduce 2 and 4. So this leaves us with 2 square root of 6 as our final answer. Now the top 2 problems illustrate another principle that's really nifty to note. Sometimes we can break down numbers and just figure out the square roots underneath the radicals. Okay? So if I took the square root of 9 divided by 25, that would be kind of weird. But I can break this apart into the square root of 9 divided by the square root of 25. And that's just going to be 3 over 5. Okay? The next thing we can do is sometimes we have numbers that are under square roots, but we notice if we put them under the same square root, and we can do this because we're just taking the square root of the whole thing, then we end up with, let's see, 48 divided by 3 is 16, and the square root of 16 is just 4. Okay? So I call this the smush it principle. I can either smush it together under one radical, like I did with this one. See, I took these two and I smushed them under one radical. Or I can take them smushed under one radical and pull them apart. Okay? Whatever happens to suit my fancy, not my fancy, but to make it able to be simplified more easily. Okay, so what we've learned, reducing radicals means looking for pairs of numbers in our factor tree that form a perfect square, because the square root of a perfect square is that repeated number. We learned how to add and subtract radicals like variables. We learned to multiply radicals and then simplifying them using this method up here. And we learned to divide radicals by multiplying the radical in the denominator by itself over itself to get rid of that radical in the denominator. We also learned the smush it principle. Okay, there are a lot of problems that you probably need to practice on this to get adept at simplifying radicals. If you have any questions, let me know.